wrap up these quantum numbers. In the last video, we looked at the first two quantum numbers. If we backtrack a little bit, the first quantum number was actually a number, 1 through 7, that identifies the energy level of the electron, or the distance from the nucleus. Is this a high energy electron that's far from the nucleus, or a low energy electron that's real close to the nucleus? The second quantum number was actually a letter. Kind of crazy, I know. It's a letter that symbolizes the shape of the orbital. The s orbitals are spherical. They're low energy. There's one of them in every energy level. So there's a 1s, a 2s, a 3s, all the way up to a 7s. And the only difference is that they just get bigger. They're all spherical shaped orbitals though. And all orbitals can hold a maximum of 2 electrons. Now there could just be one. A maximum of 2. From there we went on to the p orbitals. The p orbitals are a little bit larger than s's and they're higher in energy. So you will not find these p orbitals until the second energy level. So there's no such thing as a 1p. They have kind of this dumbbell shape. There's 2 lobes, again, which is why they're a little bit larger than the s orbitals. And there are 3 of them in every energy level, 2 and higher. They all look the same. The difference is just the way that they're situated in space, their axis in space. And again, they can all hold a maximum of 2 electrons for a total of 6. 2 in each of the 3 p orbitals. If you go to higher energy levels, the p orbitals are the exact same shape. They're just bigger and higher in energy. And the last shape were the d orbitals. D orbitals are kind of crazy. They're real high energy. There are 5 of them. But because they're larger and higher in energy, you will not find them until the 3rd energy level. There is no such thing as a 1d or a 2d. But again, they can hold a maximum of 2 electrons each for a total of 10. For the most part, they look the same. They've got these 4 lobes. The donut orbital is a little crazy, but it's equal energy to the other 4. And you can still hold a maximum of 2. And again, from one level to the next, 3rd and higher, the d orbitals just get larger and increase in energy. So those are the first 2 quantum numbers, and we just put them together kind of like this. The first would be the energy level, and the second would be the shape of the orbital. The third quantum number, it's going to be a symbol XYZ. So I get that it's weird they call these quantum numbers when they're not always numbers. Sometimes they're letters. This is going to identify the orientation or the axis in space. You won't use these with an s orbital because there is just one s orbital. But now look at the p's. Do you remember when we looked at those p orbitals and they had the axis labeled as XYZ? That's actually the 3rd quantum number. So if I go back to, like, my p's, here you go. 2pz. The z just means that it's on the z-axis in space. 2py. It's on the y-axis. 2pz. Oh, whoopsie, this one's x. 2px. It's on the x-axis in space. Right there. That's the 3rd quantum number. It identifies the axis or orientation. Oh, so now here's one thing to note. If I just saw quantum numbers 2p, and they said how many total electrons would have the quantum numbers 2p? First we'd say, can a p orbital exist in the 2nd energy level? Oh yeah, the 2p, that's legit. The p's are in every level 2 and higher. There are 3 p orbitals in the 2nd energy level. each can hold a maximum of 2 electrons. So by saying just 2p, I'm saying it could be one of 6. It could be any one of these 6 electrons. But I want to get as specific as possible. Eventually, I want to try to narrow it down to 1 electron. I want to locate one particular electron. So now let's say we add the third quantum number, 2px. Oh, okay, so we're in the second energy level. We're looking at the p orbitals, here they are. This electron is in the p orbital, second energy level, x-axis. Oh, it's one of these two. This narrows it down to 2 electrons. It's one of those 2. We're getting more specific as we add these quantum numbers. It could be the 2py, the 2pz. That third quantum number will identify one specific orbital. And that one orbital could have up to 2 electrons. Kind of similar with the Ds. But the Ds will usually have like 2 letters for their third quantum number. So they might say like, this is the 3DXY. Ah, okay. We're in the third energy level, D orbital. Yep, that's legit. So if somebody just said 3D, that could be any one of these 10 electrons. There are 5 D orbitals in the third energy level. Each can hold 2 electrons for a total of 10. But now if I put the 3DXY, it kind of shows me like the plane in space. Oh, okay, we're in the XY plane. That narrows it down to one of these 2. This could be 2 electrons. So with the D orbitals, it might be like an XY combo that's showing you the plane in space. But that's kind of the purpose of this third quantum number. It narrows it down to one particular orbital. Identifies one particular orbital. When more than one exists. So again, you won't have this XYZ stuff with an s orbital because there is only one in each energy level. So if I say 2s, that's it. There is only one s orbital in the second energy level. But if I say 2p, which of the p orbitals are you referring to? Because there are 3 of them. Awesome. So the last quantum number identifies the direction of the spin. Interesting. So electrons are always moving, and in fact, they spin. They spin and they move all over the place. When you have 2 electrons spinning in an orbital together, they will spin in opposite directions. The direction of the spin is symbolized by a plus or minus 1/2. Oh, so it kind of means it's arbitrary. But it means that one of the 2 electrons is spinning forward. Now we note that as a positive spin. One of the 2 electrons is spinning in reverse, and we'll say that's a negative spin. The main thing to know is that in the same orbital, they have to spin in opposite directions. So for example, if I say second energy level, if I just say how many electrons are in the second energy level, oh man, I got to think about like what orbitals are available in the second energy level. Okay, well the second energy level, s orbitals. Yep, it's going to have an s orbital. So there's going to be an s. The s orbital can have 2 electrons. Does the second energy level have p's? Yep, it has p orbitals. There are 3 of them for a total of 6. The second energy level does not have d's. So that's it. 2 electrons in the s, 6 electrons in the p orbitals, for a total of 8. If you just tell me that the electron is in the second energy level, that's great. It narrows it down to 1 of 8 electrons. Is it in an s orbital, a p orbital? I don't know. There's a maximum of 8 electrons that can fit in the second energy level. Okay, so now, every now and then, I'll have a freshman or even a freshman teacher that'll ask about this. Because they don't do all this crazy quantum number orbital stuff with freshmen. That's wild. Do you remember making like models of atoms and like drawing little pictures and they have like rings, or sometimes they even make them out of like gumdrops and licorice or something? And they'll always tell you, oh yeah, like the first energy level, that can hold 2 electrons. And then they'll tell you, oh yeah, the second energy level, that can hold 8. The third level, yep, that can hold 10. And every now and then, I'll have a kid that'll say, like, why? Why can I only put 2 electrons or 2 gumdrops in the first energy level? I got more room. Or it'll be a teacher, a freshman teacher that'll be like, oh, yeah, like I kind of forget. Why can I only put 8 electrons in the second energy level? And they really don't get into a whole lot of detail. Do you remember that? You're supposed to put 2 electrons in the first energy level, 8 in the second, and then 18 in the third. It all has to do with the amount of available orbitals. The first energy level only has 1 orbital, just an s. The s orbital can hold 2 electrons, that's it. There's no p's or d's or anything crazy in the first energy level. When you hit the second energy level, you can have 2 electrons in the 2s, and then you can have a maximum of 6 in the p orbitals, for a total of 8. Okay, so now we try to narrow it down. What if somebody said 2p? Now we just keep putting these quantum numbers together. Oh, is it 2p? That's 1 of 6. We've gone from 8 possible electrons down to 6. The 2p orbitals can hold a maximum of 6. Then we throw the next quantum number in there. What if they say 2py? That identifies one specific orbital. 2py? Oh, it's one of these 2. It's one of these 2 electrons right here. They're roommates. They're orbital mates. I have friends that are twins. They call each other womb mates. Get it? 2py. We've narrowed it down to 2 possible electrons. Now here's the 4th quantum number. It's arbitrary. One of those electrons is spinning forward and one is spinning in reverse. So it looks kind of like this. 2py, let's say we go plus 1/2. There's one particular electron. We're looking for the 1 electron in the 2py orbital with the forward or positive spin. And there you have it. That's the best we can do. We smush those 4 quantum numbers together kind of like an address. We're trying to locate one specific electron. Because again, when we get into like bonding and chemical reactions, we need to know the exact location of all those electrons to predict if they'll interact with electrons in neighboring atoms. It's good stuff. His partner would be this guy. 2py minus 1/2. That would be the other electron. So these guys are roommates. And they love each other. Those guys share an orbital together, but they'll always spin opposite. One spins forward, one spins reverse. Which leads us to the Pauli exclusion principle that says no two electrons will ever have the exact same set of quantum numbers. You can have 3 of them the same, but the last quantum number will always be opposite. They'll always spin opposite. Kind of like an address. You would never have 2 buildings or 2 houses with the exact same address. That makes no sense. Now they can have the same city, the same state, the same street, but the house number would be different. Kind of the same with quantum numbers. And the last thing we should mention is called the Heisenberg uncertainty principle, which says that this is the best we can do. Within this orbital, we are always a little uncertain. This is the Heisenberg uncertainty principle. We'll always be a little uncertain as to the exact location of the electron, because it's free to move. You're free to move within your house, but that address gives me a good chance of locating you. Kind of the same thing with these quantum numbers. I'm looking in the second energy level, a p-shaped orbital on the y-axis, the electron with the forward or positive spin. Now, I don't know exactly where that guy's going to be, but this is the best I can do at trying to locate one particular electron. Again, these quantum numbers, they're a good thing. We're going to use them in class. We'll review these, I promise, and we'll use some three-dimensional model kits. But they really do give us a good example of where all the electrons can be located when it's time to get to fun stuff like bonding and chemical reactions.